Hey guys, hello and welcome to week two or lesson into two of our lecture. Today we will tackle about the computer number system as well as the conversion and arithmetic operation involved in the computer number system. Now, to be honest, I do not like math, so please bear with me if um, some of the stuff or ideas presented here are too complex for you, but all the instructions have already been broken down. And later on, I will post link of other instructional materials that might help you if you are having issues with regards to the lesson. Again, feel free to ask any questions or clarifications on our Discord channel. Now let us begin. Computer number system. When we type some letters or words, the computer translates them in numbers as computers can understand only numbers. Take note, computers can only understand in the form of binary numbers, zeros and one. Okay, so if you have watched the Matrix, the concept of the matrix is that humans cannot actually interact directly with the computer, but in order to interact with the computer or the network called the matrix, data are downloaded to the human brain or passed through the matrix in the form of binary codes, zeros and one, okay, or bit code 0 and 1. Okay. A computer can understand the positional number system where there are only a few symbols called digits, and the symbols represent different values depending on the position they occupy in the number. So take note of that. Different values depending on the position they occupy in the number. The value of each digit in a number can be determined using number one, the digit, number two, the position of the digit, and number three, the base of the number system, where the base is defined as the total number of digits available in the number system. So for this topic, we are going to tackle about four different number systems: the decimal number system, the binary number system, the octal, and the hexa. So decimal, the base is 10, binary, the base is 2, octal, the base is 8, and hexa, the base is 16. Okay, decimal number system. The number system that we use in our day-to-day life is called the decimal number system. It has a base of 10 as it uses 10 digits from 0 to 9, and the successive positions to the left of the decimal point represents units, tens, hundreds, thousands, and so on. Each position represents a specific power of the base 10. For example, the decimal number 1234 or 1234 consists of 4 digits in the units position, 3 in the tens position, so this is the units position, this is the tens position, 2 in the hundreds position, and 1 in the thousands position. Its value can also be written as 1 times 10,000 plus 2 times 100 plus 3 times 10 plus 4 times 1. When you add it up, you get 1,234. As a computer programmer or IT professional, you should understand the following number systems which are frequently used in computers. Take note, guys, this concept is also important for persons involved in electrical engineering or electricity or any technology regarding electricity, not just a computer programmer or IT professional. So this is involved especially in your course. So binary number system, we have digits 0 and 1. For the octal or base 8, we have 0 to 7. And for the hexadecimal, we use 0 to 9 and letters A to F. For the binary number system, as I have said earlier, we are using two digits, namely 0 and 1. It is also called the base 2 number system. Each position in a binary number represents a zero power of the base 2, sample 2 raised to 0. And the last position in a binary number represents an x power of the base 2, sample 2 raised to the power of x. So for example, we are converting 10101 base 2 or binary 10101 to decimal. What we need to do is to split all the numbers into separate groups, and then we multiply them by 2, and then those 2 will be raised to the power of depending on the position. So for example, in the ones place, we have a power of 0. Then on the tens place, we have power of 1, so on and so forth. Now, to get the maximum power that you need to use, you just need to count the numbers. So in this instance, we have 5 numbers minus 1. So that means 4. So this number will be multiplied by 2 raised to 4, while for the rightmost number, we will multiply it by 2 raised to 0. So from right to the left side, we increase the number of power used. This is also used for the octal number system, okay, which uses 8 digits, 0 to 7, and it is called as base 8. Now, instead of using 2 raised to a number, we are using 8 raised to a number. Okay? For the hexadecimal, that is also true. We split our number into separate groups for each number, and then we multiply it this time by 16 raised to certain power depending on the number of numbers that you have. Okay, so for this one, we use, for the rightmost side, we use 16 raised to 0, and then add up one number, one base, or one power to 16 as it goes to the left. Okay, so in order for us to clarify that, let us go to the first example, which is converting 10101 base 2 or binary 10101 to decimal. So we have 1 times 2 raised to 0 plus 0 times 2 raised to 1 plus 1 times 2 raised to 2, 0 times 2 raised to 3, 1 times 2 raised to 4. So we get all the product of each and every number, and then we get the sum of those products. Okay. After getting the sum of the product, we will come up with 21. Okay, now 21 is the decimal equivalent. We can also denote this as 21 base 10. Okay. So for the octal number system, for example, we have 12570 base 8 or octal 12570. In order for us to convert it to decimal, we follow the same procedure. Okay. We multiply each and every number by 8 raised to the power of x depending on the position from the right to the left. Okay, just remember, count the numbers minus 1. So 5 minus 1 is 4. That will be your highest power, which you will use to raise your particular base. So whether that be binary 2, octal 8, or hexa 16. Okay, in this instance, 12570 base 8 is equivalent to 5496 base 10 or 5496. Okay. For the hexadecimal, take note that we are using 10 digits and 6 letters, so 0 to 9. Now, we are also using letters A to F, where A is equals to 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So all in all, those are 16 characters, 16 symbols. Take note, all the characters from right to left, okay, will start with base 0, okay, up to the number of characters that you have minus 1. So we have base 4 here. So in this instance, 19FDE base 16 or hexadecimal 19FDE is equivalent to decimal 106462 or 106462 base 10. Okay. I do have an attached Word document wherein you could actually see different examples that we have. So let's say for the binary to decimal, I have here 10100011 converted to decimal. Okay, we have how many numbers? We have 1, 2, 3, 4, 5, 6, 7, 8. Minus 1 is 7. Okay, so the highest power that we will use is 7. Then the lowest is 0. Take note, 0 is 4 whole numbers. I will show you an example later on wherein we are going to convert a number system having decimal places into a decimal number. So 10100011 is equivalent to 163 or 163 base 10. There are other examples. You can try to study them later on. We now have an example here. We have an octal number 532.2 or 532.2 base 8. To convert it to decimal, what should we do? As I have said earlier, the base 0 is used for the whole number. We are going to use a decimal for a binary, a hexa, or an octal number system, and then we are going to convert it to decimal. All the numbers after the decimal place will have a power of negative, starting from negative 1. And then if we have two numbers here, negative 2, if 3, negative 3. So in this instance, we only have 1, so we have negative 1. Okay, so we separate each number. So we have only how many whole numbers? We have 3. The maximum is 3 minus 1, 8 raised to 2. And then we have 8 raised to 0. Then for the decimal place, we have 8 raised to negative 1. So the answer for 532.2 base 8 is 3.346.25 or 346.25 base 10. Now, how about hexadecimal? How are we going to compute it? Take note, for a hexadecimal, you must convert the characters into their equivalent number in order to come up with the answer. For example, we have 1DA6 base 16. So that is equivalent to, we have 4 minus 3 times base is 3. Lowest is 0. So we have 1. 1 times 16 is to 3. D is equivalent to what? 13. Okay. times 16 raised to 2. We have A, which is 10 times 16 raised to 1, and we have 6 times 16 raised to 0. The equivalent of 1 DA 6 base 16 is 7590 base 10. Okay, there you have it, converting binary, octa, or hexa to decimal number system. Now, what would you do if you want to convert a decimal to other base system like binary, octa, or hexa? In this example, we have decimal number or decimal number 29 or 29 base 10. We want to convert it into binary. How or what shall we do? Okay, first step, divide the decimal number to be converted by the value of the new base. So, for example, we are going to convert it into binary. We divide it by 2. We are to convert it into octa by 8. If we want to convert it by hexa by 16. Okay. Next, get the remainder from step 1 as the rightmost digit or the least significant digit of the new base number. So, we are going to get the remainder. Okay. So step 1, 29 divided by 2 is 14. Okay. And then we have a remainder of 1. So that will become your rightmost number. So the result will be further subdivided again by the base number that we are using. Divide the quotient of the previous divide by the new base. Record the remainder from step 3 as the next digit to the left of the new base number. Repeat steps 3 and 4, getting remainders from right to left until the quotient becomes 0 in step 3. The last remainder thus obtained will be the most significant digit of the new base number. Okay, so again, step 1, 29 divided by 2, result is 14, remainder 1. So this will be our least most significant number. Result 14 divided by 2 is 7, remainder 0. 7 divided by 2 is 3, remainder 1. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, remainder 1. So we now have 0 as our quotient. So this will become our most significant number, and this is our least significant number. So 29 base 10 or decimal 29 is equivalent to 11101 base 2 or binary 11101. Okay. I have here another example. We have decimal number 160 or 160 base 10. We convert it to binary. Okay. So 160 divided by 2 is 80, remainder 0, which will become our least significant number. Quotient 80 divided by 2 is 40, so remainder 0. 40 divided by 2 is 20, remainder 0. 20 divided by 2 is 10, remainder 0. 10 divided by 2 is 5, remainder 0. 5 divided by 2 is 2, remainder 1. 2 divided by 2 is 1, remainder 0. And 1 divided by 2 is 0, remainder 1. So the answer will be 1, 0, 1, 0, 0, 0, 0, 0, base 2. Okay. I have other examples here if you want. Okay. What if we want to convert decimal into octal? As I have said earlier, the steps that we did for the binary number will be applied for octal and hexadecimal also if you want your decimal number to be converted into that. Okay. For this example, we have 1792 base 10 or 1792 decimal to be converted into octal. So we have 1792 divided by 8. Quotient is 224, remainder 0. 224 divided by 8 is 28, remainder 0. 28 divided by 8 is 3, remainder 4. Then we have 3 divided by 8 is 0, remainder 3. Okay, so what would be the answer? The answer is 3400 base 8. Okay, another example 127 base 10 or decimal 127 converted to octal. 127 divided by 8 is 15, remainder 7. So we have 15 divided by 8 is 1, remainder 7. 1 divided by 8 is 0, remainder 1. So we have 177 base 8. Okay. How about decimal to hexadecimal? Hexadecimal. Okay. For example, we have we have 960 base 10 or decimal 960 converted into hexadecimal. We have 960 divided by 16 is 60, remainder 0. 60 divided by 16 is 3, remainder 12. And 3 divided by 16 is 0, remainder 3. Okay, so we have 3, 12, which is A, B, C, so C, and 0, base 16. So that is equivalent of 960 base 10 to our hexadecimal. Now, how would you convert any base system to another base system aside from a non-decimal base system? So any base system to binary or octal or to hexa. For example, we have the octal number 25 or 25 base 8 converted into binary. The first step is we need to convert it into decimal or base 10. After converting into decimal or base 10, convert it into your target number, base number. So in this instance, from decimal, we convert it into binary. So first, octal convert into decimal. So we have 25 base 8 is equivalent to 21 base 10 or decimal to 1. Okay. And then you convert decimal to 1 or to 1 base 10 into binary. So divide 21 by 2. So 21 divided by 2, 10, remainder 1. 10 divided by 2, 5, remainder 0. 5 divided by 2, 2, remainder 1. 2 divided by 2 is 1, remainder 0. 1 divided by 2, 0, remainder 1. 1, 0, 1, 0, 1. That is the equivalent of octal 25 base 8 into binary. We have a shortcut method for converting binary to octal. So first, divide the binary digits into groups of 3 starting from the right. And then convert each group of 3 binary digits to one octal digit. So for example, starting from the right, we have 10101 base 2 converted to octal. So we have 101 first group. Starting from the right. So we have 101. It's the first group. And then we have, so we need to group it into three. So 0, 1. This is only 2. So we add another 0 here. That will become 0, 1, 0, 1, 0, 1. Starting from the right, again, 1, 0, 1. First group. And then second group, 0, 1. And then there's no preceding number here. So we add 0. Okay. So in order for us to group it into three. So we convert each and every number into a digit or octal equivalent. 0, 1, 0 binary to octal is 2 base 8. 1, 0, 1 is equivalent to 5 base 8. Okay. So what happens after that? You just concatenate the two. So that is 25 base 8 to 5 base 8. So 101 01 base 2 or binary 101 or 10101 is equivalent to 25 base 8. How about octal to binary? Octal to binary. Convert each octal digit to a 3-digit binary number. The octal digits may be treated as decimal for this conversion. And then combine all the resulting binary groups, 3 digits each into a single binary number. For example, we have 25 base 8. Convert it into binary. First is convert each octal digit to a 3-digit binary. So 2, split, and 5. 2 base 10, 5 base 10. So we convert it into binary. 2 base 10 is 0, 1, 0 base 2, and 5 is 1, 0, 1 base 2. And then after doing that, just drop the or concatenate the two numbers and then retaining the base 1, 0, 0, 1, 0, 1 will be the binary equivalent of 25 base 8. How about binary to hexa? First is divide the binary digits into groups of 4 starting from the right. Then convert each group of 4 binary digits to one hexadecimal. So in this example, we have 1, 0, 1, 0, 1 base 2. So we break it into 4 starting from the right. So we have 0, 1, 0, 1. That's the first group. And then the second group is 1. So we need 4 numbers. So we have 3 zeros and then 1. 3 zeros and then 1. Convert this into decimal. Okay. Sorry. Convert this into hexa. Okay. So 1. Convert it into hexa. So we have a wrong base here. I will leave. Okay, sorry for the typo. So we convert 0001, 0101 into hexa. Okay. So after doing that, we get 1 and 5. And then we just need to concatenate the number. Okay. We also have hexadecimal to binary. In order for us to do that, first is to convert each hexa to 4-digit binary number. And then we combine all the resulting binary groups, 4 digits each, into a single binary. In this instance, we have 1, 5 base 16. We split it into 2. Then after splitting it into 2, we group it into 4. So 1 equivalent to 0001. base 2, 5, 0, 1, 0, 1, base 2. After getting that one, we just concatenate. So we have 0, 0, 0, 1, 0, 1, 0, 1, base 2. So that is how you will convert your number system. Okay, computers, data, and information. Data can be defined as a representation of facts, concepts, or instruction in a formalized manner, which should be suitable for communication, interpretation, or processing by human or electronic machine. It is represented with the help of characters, such as alphabets, digits, or special characters. Binary code, on the other hand, refers to when numbers, letters, or words are represented by a specific group of symbols. It is said that the number's letter or word is being encoded. The group of symbols is called a code. The digital data is represented, stored, and transmitted as group of binary bits. This group is also called as binary code. The binary code is represented by the number as well as alphanumeric letter. What are the advantages of binary code? Following are the advantages. They are suitable for computer, they're suitable for the digital communication. They make the analysis and designing of digital circuits if we use the binary. Since only zeros and one are being used, implementation becomes simplified. Classification and classification of binary codes. So the codes are broadly categorized into the following four categories. Actually, this is five. Classifications are weighted codes, non-weighted codes, binary coded decimal, alphanumeric, and arithmetic. Weighted codes are binary codes which obey the positional weight principle. Each position of the number represents a specific weight. Some systems of the codes are used to express the decimal digit 0 to 9. In this code, each decimal digit is represented by a group of 4 bits. In this example, decimal 24 is expressed with positional weight of 8, 4 to 1. So for each number, 4, 4 to 1, 4 2, we have 0, 0, 1, 0, and for 4, we have 0, 1, 0, 0. Non-weighted codes in this type of binary code, positional weights are not assigned. Examples are XS3 and Greek code. XS3 or XS-3 code is a non-weighted code used to express decimal numbers. They are derived from the 8421 BCD code words, adding 0011 base 2 or 3 base 10 to each code word in 8421. Okay. The XST codes are obtained as follows: decimal number converted into 8421 BCD, add 0011, so you have 3. Okay. We have decimal 0, BCD, add 0011, that is the XS3 equivalent. Basically, convert decimal into BCD equivalent, and then in order to obtain XS3, you add 0011 from the BCD. Gray code. Gray code is an unweighted code, and it is not an arithmetic code, which means there are no specific ways assigned to the bit position. It has a very special feature that only one bit will change each time the decimal number is implemented, as shown in this figure. As only one bit changes at a time, the gray code is called the cyclic distance code. It is a cyclic code and cannot be used for arithmetic computation. Okay. Application of gray code or uses of gray code are used in shape position encoders, which produces a code word which represents the angular position of the stack. BCD code. In this code, each decimal digit is represented by a 4-digit or 4-bit binary number. BCD is a way to express each of the decimal digits with a binary code. In the BCD, with 4 bits, you can express 16 numbers 0000 to 11111, but only the first 10 are used 00002 1001. The remaining six codes 1010 to 1111 are invalid in BCD. So basically we're only using zeros to 9. Advantages, it has very similar pattern to decimal, and we need to remember binary equivalent of decimal numbers 0 to 9. The disadvantage are they have different addition and subtraction rules. Arithmetic is a little more complicated, and it needs more number of bits than binary to represent the decimal, so it is less efficient than binary. Alphanumeric code is a binary digit or bit that can represent only two symbols, as it only has two states, zeros and ones. It is not enough for communication between the computers because we need many more symbols for communication. The symbols are required to represent 26 alphabets with capitals and small letters, numbers from 0 to 9, punctuation marks, and other symbols. Alphanumeric codes are the codes that represent numbers and alphabetic characters. Mostly such code also represent other characters such as symbols and various instructions for conveying information. They should at least represent 10 digits and 26 letters of the alphabet, totaling 36 items. The following three are alphanumeric codes that are commonly used for data representation. We have the ASCII, the ABCDIC, and 5-bit Modo code. ASCII code is a 7-bit code where EBCDIC is an 8-bit code. ASCII code is more commonly used worldwide, while EBCDIC is used primarily for large IBM computers. Error codes. These are binary code techniques available to detect and correct data during transmission. Code conversion. We can convert binary to BCD, BCD to binary, BCD to XST, and XST to BCD. Binary to BCD conversion. These are the steps. Convert the binary number to decimal, and then step 2, convert the decimal number to BCD. For example, we have 111101 base 2, or binary 1111 to BCD. First, you convert the binary to decimal, so we will come up with 29 or 29 base 10. After doing that, convert the decimal number to BCD. How do we do that? We split the numbers or the characters, okay, into each and separate digit. Okay, you group the separate digits into 4 binary digits. So I get the equivalent of 2, the equivalent of 9 in binary. So we have this one. After that, all we need to do is concatenate and then append BCD. Okay, that is how simple you would convert binary to BCD. Okay, next, BCD to binary conversion. You convert the BCD number to decimal, and then after that, convert the decimal to binary. For example, convert BCD to binary. So first, convert each 4 digit into a group and get the decimal equivalent for each group. 1, 2, 3, 4, first group. Second group, 1, 2, 3, 4. Convert it into, or get the decimal equivalent. So this is 2, this is 9. Concatenate, we have 29. Then, after doing that, convert the number into binary. How do we convert decimal into binary? Divide it by 2. So the equivalent will be 11101 base 2. Okay. How about BCD to XS3? Okay. To convert BCD to XS3, first convert BCD to decimal. Next, add 3 base 10 to this decimal. Convert into binary to get XS3. Okay. First, convert BCD to XS3. We have 0110 BCD. Convert it into decimal. So the equivalent is 6. Plus 6 base 10. Add 3 base 10 to decimal. So C, 6 base 10 plus 3 base 10 is 9 base 10. 9 base 10 converted into binary. So we have 1, 0, 0, 1. So decimal to binary. How do we do that? We divide it by 2. So this will be the result. Okay. And then just replace the base into XS3. How about XS3 to BCD? First, subtract 0011 base 2 from each 4-bit of XS3 digit to obtain the corresponding BCD. Example, convert 100, 1110, 10 XS3 to BCD. Okay, so this one, then you convert, you subtract 0011 base 2 to convert it also to 4-bit. Okay, so convert it into 4-bit. So we will come up with this one, 0 minus 1. Answer is 1. Because we carry over 1 from here. This is basically binary arithmetic. So later on, I will show you how binary arithmetic is done. Basically, this binary arithmetic, and then we will come up with this answer, which we will concatenate again, BCD. Do not be bothered with the BCD to XST conversion, as I will not uh, include complex examples in your exam. So do not worry about it. We are just here to discuss how the processes are done. In fact, most, if not all of these calculations are already in the internet. You can find calculators in order to convert one base number to another. So you just need to know how the process is done. Complement arithmetics. Complements are used in digital computers in order to simplify the subtraction operation and for the logical manipulation. For each radix R system, radix R represents the base number of number system. There are two types of complement, the 1 and the 2. So first one is the radix complement, referred to as the R's complement, and then the diminished radix complement refers to the R as the R minus 1 complement or R dash 1 complement. Binary system complement. As the binary system has a base R is equals to 2, so the two types of complements for the binary system are 2's complements and 1's complement. For the 1's complements of a number is found by changing all 1's to zeros and all zeros to 1. This is called as taking complements or 1's complement. Example of 1 complement is as follows. Given the number 10101, if I will ask for the 1's complement, you just flip 1 into 0 and 0 into 1. So the equivalent is 0, 1, 0, 1, 0. For the 2's complement, for binary number, it is obtained by adding 1 to the least significant bit, 1's complement of the number. 2's complement is equal to 1's complement plus 1. Example of 2's complement is as follows. Take note. Given the number 10101, the 1's complement 01010. Okay, in order to get the 2's complements, you add 1 to the 1's complement, starting from the least significant bit or least significant number. So 0 plus 1 is 1. Okay, and then 1, 0, 1, 1. You just bring it down. Why? Because basically all of the following or all of the preceding numbers will become 0. So the answer will be 0, 1, 0, 1, 1. Okay. So again, that is 1's complement and 2's complement under the binary system. For the binary arithmetic, It is an essential part of all the digital computers and many other digital systems. For the binary addition, we have the following table rules. It is a key for binary subtraction, multiplication, and division. The four rules of binary addition are: case number one, a plus b. If a is 0 and b is 0, the sum is 0. Okay, we do not carry anything. Case number two, if a is 0 and b is 1, the sum is 1. We do not carry anything. If a is 1, b is 0, the sum is 1. We do not carry anything. If a is 1 and b is 1, so the sum is 0, okay, we carry over 1 to the next significant bit. Okay, so for example, in the fourth case, a binary addition is creating a sum of 1 plus 1 equals 10, i.e., 0 is written in the given column and they carry over 1 to the next column. For example, we are adding 0011010 and 001100. The answer will be 01001110. Okay, so how did it come to this? 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, carry over 1. So 1 plus 1 plus 0 is 0, carry over 1. 1 plus 0 plus 0 is 1. 0 plus 0 is 0. Okay, I have another example here which you can find on one of the video links that I will upload at the beginning of this lecture. So for binary addition, take note, the fourth rule is 1 plus 1 is 0, carry 1. Okay. If you do 1 plus 1 plus 1, your answer will be 1, carry 1. Okay. So for example here, 1 plus 1 is 2. Okay. 1 plus 1 is 2, which is basically what? 1 is 0. 2 is basically 1, 0. Okay. Next, if we add 1 plus 1 plus 1, that is 3. That's basically 1, 1. Okay. 1, 1. We have 1, 2. Okay. The weighted here is 1, 2. 1, 0, 2 is 1. Weighted value here is 1, 2. That's 1, 1. So that is 3. Okay. Binary addition, another example. We have this example. We have 0, 0. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 1 plus 1 is 1, carry 1. The answer is this one. Another example. We have here 10. But this is the weight. Okay. So that you will not be confused. This is the weight. Okay. So 10 plus 14 is 24. How do we get that? 0 plus 0, 0. 1 plus 1 okay, is 0, carry 1. 0 plus 1, okay. Sorry. 1 plus 1 is 0, carry 1. So 1 plus 1 is 0, carry 1. 1 plus 1 plus 1 is 1, carry 1. So if you add that up, value 16 plus 8 is 4. Okay. How do we do that for decimal places? Symbol applies. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 0 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. Okay, so I hope that is clear. If not, there are other links that I have provided with regards to binary addition and subtraction. Subtraction and borrow. These two words will be used very frequently for the binary subtraction. There are four rules for binary subtraction. Namely, 0 minus 0 is 0, 1 minus 0 is 1, okay? 1 minus 1 is 0, 0 minus 1 is 0, borrow 1. So for example here, 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 1 is what? 0 minus 1 is 0, borrow 1. So we need to borrow, that becomes 1, it becomes 0, 0 minus 1, borrow 1 again, this becomes 1, this becomes 0, 0 minus 0 is 0, 0 minus 0 is 0, 0 minus 0 is 0. Okay, so what happens here is that if we are doing subtraction, you borrow 0 minus 1 borrows 1 from the next or the next significant bit. Okay, so that becomes 0 minus 1. Okay, becomes 0, but we are borrowing 1, so that becomes 1. Okay, 1 with borrow. Okay, 1 with borrow. I think, okay, we need to correct this particular table. So that should be 0, 1, 0, 1 with borrow. Okay, I will correct this one later on. So another example here is for binaries. We have these rules. Okay, so for binary subtraction, we have an example here. Again, the weight is shown. Okay, so another binary subtraction example. In this example, we have 1, 1, 0, 0 minus 0, 1, 1, 1, 1. So what happens here? Remember that 0 minus 1 is 1. 1, borrow 1. But in this instance, notice that we are borrowing from this position, which is also 0. So what will happen? So what happens is like this. 0 is borrowing 1 from this value. Take note, we are base 2. So basically, the values that we are borrowing is 2. Okay, so that would be more simple. Think of it as we are borrowing actually 2. Okay, the 0 minus 1 cannot be, so borrow 1, which is 2 times 1 from here, which is also cannot be. So we are borrowing from this one, which is 1. So this becomes 0. Okay, so we were able to borrow 1 here. So this becomes 2. Okay, take note. This becomes 2. So we are now able to borrow 1 from here. So we are borrowing 1. So this becomes 1. And then this becomes 2. Okay. So 2 minus 1 is 1. 1 minus 1 is 0. And then this becomes 0 minus 1. So cannot be. So we borrow from here. So this becomes 2. Okay. 2 minus 1 is 1. Okay. So that is how you would think of it. Okay, so in this example, 1, 0, 0, 0, 0 minus 1, 1, minus 0, 1, 1, 1, 1. Okay, 0 minus 1 can be, so borrow 1 from here. Cannot be, because this is 0, so borrow 1 from here. Cannot be, so cannot be, so borrow from here. So this becomes 2. Okay, but it will borrow from here. This becomes 1, this becomes 2. It will borrow from here. This becomes 1, this becomes 2. But it will borrow here. This becomes 1, this becomes 2. Okay, 2 minus 1 is 1. 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 1 is 0. 0 minus 0 is 0. So that is how you would subtract binary numbers. For binary multiplication, this one is a little bit more, it is a little bit more simple. There are four rules. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. For example, we are multiplying 0, 0, 1, 1, 0, 1, 0 to 0, 0, 1, 1, 1, 0, 0. The answer will be like this. Okay? So if you are multiplying zeros as your last number, you drop those zeros. You just drop those zeros. All you need to do is to multiply all the numbers that are not zero preceding the ones. So meaning to say we only need these four, but not the first numbers with zeros. So we just multiply 0, 0, 1, 1. And then after that, we just add so 0, 0, 0, 1, 1, 1. 1 plus 1 is 0. Carry over 1. 1 plus 1, 0. Carry over 1. Okay. 0 plus 1 is 1. Then 0. So this will be the answer. Okay. For the division, the similar to decimal division, it is called as the long division procedure. All you need to do is to divide given the numbers. So for example, okay, so for binary division example, suppose we have here this number to be divided by this number. So first we remove the preceding zeros, okay, from the most significant bit. After doing that, so we must compare this. In this instance, we will compare the number of bits to the number of bits in the dividend. Okay, we compare the divisor from the dividend. So we check if it is greater. If the dividend is greater than the divisor, we add 1. Okay, if not, that is 0. After that, you multiply the answer, it's either 1 or 0, to the divisor, and then subtract it from our answer. Then you bring down the next bit, and then you compare again if it's greater than, and then up until the divisor, or up until the remainder is 0. So in this instance, for example, 11 greater than 10, that is true. So 1, 1 times 10 is 10. So 1 minus 0 is 1. 1 minus 1 is 0. Bring down the next one, so 11. 10, that is true. So 1 times 10 is 10. 1 minus 0 is 1. Bring down 11. 1 times 10, 8. 1. Bring down again 11. 2. So 1 times 10, 1. Bring down 0. 10 divided by 10. 1 times 10, 0, bring down 0, 0 greater than 10, that is 0. 0 times 10 is 0. So the answer would be 11111 0. So in this another example we have here 101101 divided by 101. First, we get the number of digits. So 101 greater than or equal to 101. So that is true. 1 times 101. Okay. If you bring down, in this instance, of course, we can check the next one. So 1 greater than 101. So that's 0. 0 times 101 will become 0. 101, sorry, 10 is greater than 101. So again, that's 0 times 101. So that's 0. You bring down again 1. 101 is greater than 1, greater than or equal to 101. So that's 1 times 101. That becomes 0. So the answer is 1001. For this example, we have then remove 0, so 110. 101 is greater than 110. Okay, so this example, please notice that the numbers are not aligned, so you might get confused. So first, as I have said, divide it and compare with the same numbers or the same digits. So 110 is greater than 101, so that's not true, so that's 0. 0 times 110 is, of course, 0. So you bring down the next number. So 101, 0, you bring down the next number is 1010. It's greater than 111, that's true. So 1 times 110, so 110. You subtract. The answer is 100, bring down 1. It's greater than 110, that's true. 1 times 110, 110. You subtract, bring down 0. 110 is greater than equal to 110. That's true. 1 times 110 minus 110 is 0. So the answer is 111. Again, this is another example. We have here 110 is greater than 101. So that's true. So 1 times 101 times 101. The answer is 1. Okay, bring down the next number. So that's 11. 11 is greater than 101. So that's false. 0 times 101 is 0. 11, bring down 0. So 110 is greater than 101. That's true. 1 times 101. 101 minus 101. The remainder will be 1. Okay. So the answer is, 101, but we have a remainder of 1. Okay. So that is how you would do a binary division. Octal arithmetic It uses 0 to 7. Okay. So octal arithmetic can be addition or subtraction. So it's not that uh, hard. So it's just like binary addition and subtraction. So always remember that we are dealing with um, the value of 8. Okay. From binary, we are dealing with the value of 2. Okay. For this example, we have 456 base 8 plus 123 base 8. The answer is 601 base 8. How did that happen? So we just add 6 plus 3 is 9. Okay, so take note, we only have base of 8. And say this one has an excess value. Okay, so 6 plus 3 is what? 9. And that is over our defined value. Okay, so in this example, we have here, okay, just go and take a look at this, the table. We have here 7, 8, 9. That becomes, notice 11. So 1 over 1, 5, 6, 7, 8, 8 already over our values. 8 is 0. Sorry, 8 is 10. So 0 over 1, 4, 5, 6, 601. Okay, again, 6 plus 3 is 9, 7, 8, 9. That is 11. 1 here over 1, 5, 6, 7, 5, 6, 7, 8, 0, 7, 8. So that's 10, 0 here over 1, 4, 5, 6, 601, or 385 as a decimal equivalent. How about subtraction? We just borrow 8. Okay, so in this example, 6 minus 3 is 3, 5 minus 7. So cannot be borrow 8. So that becomes 8 plus 5, 13 minus 7. So that is 6. 4 becomes 3. 3 minus 1 is 2. Okay. For hexadecimal arithmetic, it is or it follows the same concepts. However, take note that we are also dealing with letters A, B, C, D, E, F, which translates into the values of 10 to okay, 10 to 15, okay, 10, 11, 12, 13, 14, 15, okay. So in this example, we have 4. Okay. In this example, we have A plus 5, B 16 is equals to F by 16. Okay, we basically have 11 plus 5, okay, is F, sorry, A, which is 10 plus 5 is 15, which is F, okay. 6, in this example, we have 4A6 plus 1B3, 4A6 plus 1B3, 6 plus 3 is 9, A is 10 plus B is 11, A is 10, A plus B is 11. So that is equivalent to 10, 11, 21, 21, 19, 20, 21. Okay, so for this one, we are going to use the table. For example, 6 plus 3. So we just use the table to get the value. So 6, then 1, 2, 3. So that is 9. So 6, 3, answer is 9. And then A plus B, the answer is 15. So 5, carry over 1. 1 plus 4, 5 plus 1 is 6. So 6, 5, 9. For the subtraction part, so we have here 4 is 6 minus 1 be 3. 6 minus 3 is 3. 16 A, sorry, 6 minus 3 is 3. A minus B cannot be. So we borrow 1 from 4. So this becomes 3. Then this becomes plus 16. So 9, 10, 26. 6 minus B. Okay, let us check if this is correct. 26 minus B, 11. 6 minus 11, 15, or F, right? 15 is F. Okay, 15 is F. K minus 1 is 2. Okay, 6 minus 3 is 3. A minus B cannot be. Borrow 1 from 4, so 4 becomes 3. And A equivalent is 10 plus 16, 26 minus B, which is 11. 26 minus 11 is 15, which is F. So I'm not quite sure why in this particular calculation it's a table. Anyway, that is how you will do the hexadecimal subtraction. Again, take note for addition, 6 plus 3, 9, A plus B, which is 10 plus 11. Okay. For this one, we use the table, but for the subtraction, we carry over the value of your base. So for hexadecimal, the base is 16. For octal, the base is 8. For binary, the base is 2. Okay, so that is all for now. Thank you guys. And I'm sorry if I'm not able to deliver that concise information that you want. But as I said, I've linked materials from YouTube. You can search for other YouTube videos about this concepts and lecture if you want. And you can post your questions in our Discord channel. Thank you and have a good day.